Okay, where do we use all of these derivatives? Where do they come into play? How do we use them? Well, now this depends on your field of study. So depending on what you are choosing to do, there's a derivative in there somewhere. Derivatives were developed primarily to figure out the mathematics necessary to do physics. So let me start there. We already have a bunch of particularly named derivatives. If I have a position function, S of t is where I am at time t, then the derivative of that is change in position with respect to time. What do we call that? Velocity. And the change in velocity with respect to time, acceleration. Page 235, problem number 9. I'm not even going to make one up. Let's just pull one right out of the book. The height in meters of a projectile shot upward from a point 2 meters off the ground with an initial velocity of 24.5 meters per second is. All right, wait a minute. The height of a particle projectile shot vertically upward from a point 2 meters above the ground. With a starting velocity of 24.5 meters per second is h equals 2 plus 24.5 t minus 4.9 t squared meters. T in seconds. Whew. Okay, now I have the problem in front of me. What is the velocity of the particle at time 2 and at time 4? An instantaneous velocity. If my projectile had a speedometer on it, what would that read at exactly 2 seconds after launch and exactly 4 seconds after launch? How do I get there from here? Height would be my position equation, so I need the derivative to get the velocity. Velocity at time t is h prime of t, change in height with respect to time. What is the derivative of this equation? Because the t squared becomes a 2t, the t to the first becomes a 1. Plug in 2, plug in 4. What do you get? Now I am going to make a hopefully not unreasonable assumption here. We launched our particle from a height 2 meters above the ground with an upward velocity of 24.5 meters per second. And the two numbers in my equation, the 2 and the 24.5, are positive. I'm going to assume positive means up and negative means down. So at 2 seconds, we're going up. At 4 seconds, we're coming down. Great. Make sense? If I launch my particle upward, at some point in time, got to come back down. It was going up at time 2, it was coming down at time 4. So what happened in the middle? The velocity hit 0, which means, Blake, it stopped. If it stopped moving, that's as high as it's going to go. 2 questions. When did it stop? What is the maximum height? Let's start with the first one. When do we hit our maximum height? Whenever my velocity is 0. That's where we stopped. That's what we say. Okay, so I want v of t to be equal to 0. All right, well, there's my equation for v of t right there. Move it over. Negative 9.8t is negative 24.5. So t is 24.5 divided by 9.8 because the minus signs cancel. $2.5. Before I go any further, does this make sense? At time 2, we were moving upward with a velocity of 4.9 meters per second. At time 4, we were coming down with a velocity of 14.7. That's much faster, isn't it? So we must be closer to stopping at time 2 than we are at time 4. So coming up with 2.5, I think that's okay. By the way, I really should have units on all of this. So this 2.5, what unit goes with that? Because that's time. I'm up there somewhere. How high? Say that again, Jolanta. Plug the time into the original equation. The original equation told me height. I know when it's there. I go back up to that height equation. And now what I'm asking for is h of 2.5. Once it happen? That's up there. But we know at 4 seconds we were coming back down. Velocity was negative. When do we hit the ground? How fast are we going when we hit it? I'm sorry, say again? Yeah, because we said we launched it from 2 meters above the ground. No, I want to know when I hit the ground. I launched from up here. When do I hit the ground? I launched from a height of 2 meters. I'm not 2 meters tall, so that's a little bit above my head. Yes. Is what -2? No, because I took the 2 into account up here, right? The height includes the 2 that I started with. The velocity of 0 told me when I stopped. I was moving up. I'm not going to just gently land on the ground, am I? I mean, that's going to hurt. Patrick? No, it's based off the ground. I started 2 meters above the ground. So the height needs to be 0 when I find out, right? To know when I hit the ground, I need to know when the height is 0. So I take my height equation and set it equal to 0. I think I better, because that is a quadratic equation being set equal to 0. If I want to know where a quadratic equation is equal to 0, I do the quadratic formula. If you really want, you could complete the square or factor. I think I'd rather drill my own teeth. I'm going to rearrange this equation, though. I'm going to put it on the other side. 4.9 t squared minus 24.5 t minus 2. I don't like having the first number be negative. Negative 4.9 t squared. Remember, it's got to be in order, t squared, then t, then constant, for me to use the quadratic formula. So t is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. I am not a lab scientist. Sig figs are for lab sciences. If I really want to be pedantic here, I should only have 3 significant digits. 24.5 was the most significant digits I had in any of this. So I would end that at 25.3. I don't care. I'm a math geek. I'm going to keep all of the numbers until the very end. I won't bother with sig figs until the last step. Notice what happens if I subtract. I'm going to get a negative number. What the? Why would one of my t values be negative? Because it's a parabola, right? The quadratic gives me a parabola. It's going to have an x-intercept here and an x-intercept here, but I started up above. So in order for me to go down on the left, I have to go back in time. I started at 2 meters up. So if I run the clock backwards, I would be on the ground. I don't care about that. I started at 2 meters up. I only care about the positive one. So let's just add. I can ignore the negative one safely. Mm-hmm. 5.08. 5.08 seconds. Now, a lot of people will tell me, oh, I was at the highest point at 2.5. I should be back down at 5. But I'm not on the ground at that point in time. At 5 seconds, I will be back where I started at 2 meters. I still have to make it to the ground. Okay, how fast was I going when I hit the ground? I take this time, 5.08 seconds, and I put it in my velocity equation. Helps if I try to put it in the right equation. Okay, I'm an American. 25 meters per second doesn't mean anything. How fast is this? Get on the internet, grab your phone, look up the unit conversion, turn this into miles per hour. How fast am I going when I hit the ground? I think 7 meters a second is 15 miles an hour. I should be doing about 45, 50 miles an hour when I hit the ground. What's the unit conversion? 56 miles an hour. Ow! This is my problem. I don't intuitively understand meters per second, but that's a number I understand. A lot of science questions, we run into this problem. I get an answer in a physics class of 32 meters per second squared. What does that mean? I get 320 joules. What the hell's a joule? I've got to convert this into a unit that matters to me, that I can intuitively understand. Meters per second isn't it? But that's me. I was raised here. If you are raised overseas and intuitively understand meters per second, leave it just like that. It's fine. All of my Canadian friends, go for it. How far did we go? Well, in the only direction we went up and down. If that's my X direction, that's fine. But how far did we travel? You actually don't need to do any calculus to answer that question. That tells me how far my displacement is. And even that's not correct because I started 2 meters up and I ended on the ground. So initial position minus final position is 2 meters. But I asked how far I traveled. What do you got for me, Colin? No, you were going to answer the other way. Displacement is where I ended minus where I started. And in this case, I ended at 0, I started at 2, so my displacement is 2. But I asked how far I went. Again, that's not quite correct.
The maximum height plus maximum height times 2.
I need to take the maximum height because I went from the maximum height down to the ground. And then I need to take the maximum height from the point I started, which was at 2. So I have to subtract 2, not add 2. I started here at a height of 2. That's at time 0. I hit a maximum height, which we said was 32.625 meters. And then I went all the way down to the ground. So I went 32.625 down and 30.625 up. There's no calculus required for this. I just have to measure properly. I once asked the question about hitting a home run. If you hit a home run, how far did you go? Well, I started at home plate. I ended at home plate. I went 0. No, that's your displacement. If you don't do all 360 feet, that home run doesn't score. Questions? Yes, ma'am.
For the fourth segment, can you put something about like you never really like around 2 meters?
Oh, I said if we were at time 5, I went up 2.5, I should come down 2.5. But that's up and back down to where I started. That's why there's that extra 0.08 seconds to make it to the ground. Because at time 5, because it only took me 2.5 to go up. So 2.5 to come down, I'd be back where I started, right up here at height 2. In a very real sense, every piece of calculus kind of descends from this basic kinematics idea. The physics of motion becomes the physics of a lot of things. When we talk about a vibrating string or a pendulum, then we're talking about a second derivative because we know the spring behaves with that sort of behavior. The force is proportional to spring constant times distance stretched, but force is mass times acceleration. So I get acceleration equations instead of velocity equations. Here's a piece of wire. If I hook this wire up to a wall socket or a lamp or something like that, I have electricity moving, right? The quantity of electricity on a spot in this wire, Q of T, charge at time T, right here at this little plate. I can measure that. Unfortunately, the units for charge are coulombs. It's named after a person. Every unit in electromagnetics is named after somebody. Bugs the snot out of me because you never remember what the hell the units are. Coulombs is a certain number of electrons per cubic meter. But I think about the electricity moving. So I'm going to measure the change in charge with respect to time. That would tell me how much electricity goes past that spot. How do you measure that? I physically clamp to either side of this spot another wire and run the same amount of electricity through that piece of wire as well, and I measure the moving charges. That's called current. And that's amps. Named after ampere. So in a sense, every discussion of electricity is exactly like looking at little moving blocks. Page 228. My electrons flowing past a point in my wire. If you really want to be pushy about it, the electrons are moving in one direction and the positive holes that they leave behind are moving in the other direction. And that's why electricity has a positive terminal and a negative terminal. It's which way are things going. From minus to plus is the directions my electrons flow. We were just talking about this at lunch. I hate electricity. Electricity scares the fuck out of me. I went to change a lamp, a fixture in my house. So I go down to the basement and I say, oh, kitchen, turn off the kitchen. I go upstairs and I unscrew the fixture and I put in a new fixture. Now I'm not going to bonk my head on the hanging light. I put up a fixture that's flush to the ceiling. While I'm at it, this switch on the wall that controls this sparks. I'm going to go change the switch. The switch has been off while I was working on the light, but the basement, the breaker has been off. So I go to unscrew the switch and I pull the switch out and that is rusty. That's why it keeps sparking. So instead of unscrewing it, I'm going to cut it. So I grab my cutters and I go snip and it goes zzz, and it arced a hole in the side of my cutter, about the size of a pencil eraser. Because even though the kitchen was off, the light switch was on the circuit in the next room. I'd gotten lucky working on the ceiling because the switch on the wall had been off. That circuit had been live the entire time. I went down and shut off the whole house and finished the job. And then went through and reset every clock in the house. But electricity's scary, man. But I don't care what field of science or anything you're studying. Let's get out of chemistry. Let's get out of physics. Let's go to biology. Let's go to chemistry. Chemistry, I can talk about reaction rates, right? Let me see if I can remember this formula. I forget what the actual product is, but there's also oxygen gas liberated. Potassium nitrate and manganese dioxide are two black powders. They're basically indistinguishable from one another if you just look at them. Potassium nitrate, manganese dioxide, you mix them together, you heat them very slowly, and you get oxygen gas. The product, it could be. My chemistry is a long time ago. I did this experiment in a year that starts 198. It's been a while. So potassium manganate, KMNO3. Okay. I don't know if it's 1 or 2. That's why I don't remember in the oxygen. I don't remember if it's 1 or 2 charged. So I don't know what this is. That's for the chemistry class. You guys can figure that out. Oxygen, but is potassium's a 1? Is manganese a 1 or is manganese a 2? I don't remember. Who's got the periodic table? Guys, deal with this later. That's not the important part. It's +4. So somewhere, so I'm being wonderful. No. No, it's got it. I have no idea. All I remember is they called it manganese dioxide, so I'm remembering that part. So here's the deal. You take this powder, you heat it in a test tube. You take a stopper with a hole in it, you cork that and run it upside down into a water column, and you liberate pure oxygen gas. The rate at which you apply heat changes the rate of the reaction. There's a catalyst here. And that catalysis is a derivative. It's telling me how the rate of the reaction is changing. I will tell you that in order to best do this experiment, you should have a large surface area, because the oxygen is liberated equally from the surface of the powders. So you mix the powders, you put them in a test tube. Rather than do the test tube vertically, I positioned the test tube almost horizontally. Clamped it in clamp, and sat there with a nice wide flame diffuser, diffusing the flame, waving it back and forth so it would heat very slowly. In order to prevent the powder from spilling out, you use a steel wool bundle in front of your stopper. That way the powder doesn't spill into the tube. One problem: high oxygen environment plus flame equals, yeah, boom. I was not very careful in using my diffused flame, and my steel wool caught fire. The test tube shot across the room and embedded itself in the wall at the other side of the lab. Yes, don't do this, people. Catalysis is a derivative. Reaction rate is a derivative. The rate at which you generate product based on the amount of each. I know the stoichiometry lessons are still sitting there, people. You've done this before. But it's a derivative. Diffusion. How fast does a chemical spread? Here's one of my favorite derivatives. My neighbor likes kimchi. I hate it. More power to you. If you like kimchi, great. I'm about to abuse your taste buds. She gives me some kimchi. I'm not going to eat it. It gets thrown out. So my kimchi is in my trash can, stinking up the room. There are two different derivatives we can take here. We can take the derivative with respect to distance. The trash can is back there. Look, it's behind the door in the corner. There's the trash can. Which of us smells the stink more, Evan or me? So this derivative, is this negative or positive? As distance increases, does the stink go up or down? The farther away I am, the stronger it smells, or the closer I am, the stronger it smells? The closer I am, the stronger. So the further away I get, this is a negative derivative. I don't know anything about any function at all, but I know this should be negative. There's another derivative we can ask. I can ask about the derivative of stink with respect to time. What happens the longer this stuff stays in my trash can? The worse it gets, right? So is that derivative positive or negative? As time goes on, the stink gets worse. Now, if you like kimchi, feel free to use something else, like, I don't know, Limburger cheese or a 3-day-old fish. Take whatever you think is the stinkiest object, put it your neighbor's daughter's newborn baby. That's a horrible trash can, right? The diapers are a bad thing, not the baby itself. I'm not throwing out a baby. I don't have any formulas at all, but there's a derivative in the middle of my work. Med micro time. Medical microbiology time. Here I have a number of bacterial colonies in my petri dish. I look, I count. Colonies have to be a particular size to count, so we measure appropriately. There's this grid you put over the petri dish. You count the number of grid squares that are occupied. So let's assume that at some time I count and there are 20. And I know that this particular bacteria reproduces asexually. And so in a day, the number of colonies is doubled. And in another day, it'll do it again, right? I can write a growth rate equation. The population at time t is 20 times 2 to the t. Now, again, I'm going to tell you I don't like the way this equation is written because what is my favorite base? E. I don't want to work in base 2. I want to work in base E. So I'm going to change that, and I'm going to write this as 20 times e to the ln2 t. So now it looks like e to the number t. I'm happier about that. If you like leaving it as 2, that's fine, but we're going to have to take a derivative here. How fast is this bacterial colony growing on day 5? I'm not asking how many colonies there are on day 5. I'm asking for the rate of change, the growth. As soon as I hear that phrase, that's a derivative. I want dp dt at 5. This is why I rewrote it to be e, because then I can take the derivative in an easier fashion. The derivative of e to the stuff is, but wait, there's more. What goes in my chain rule parentheses there? The derivative of the stuff. The stuff is number t. The derivative of 3t is 3. The derivative of 7t is 7. The derivative of log 2t is log 2. ln2 is a number. If you really want, you can rip out your calculator, grab that, give me the decimal. ln of 2 is 0.693147. Use as many freaking decimal places as you like. It doesn't matter. It's a number. I took its derivative. What do I do with that piece of information? Plug in 5. Twenty e to the ln2 times 5 times ln2. My bacterial population is increasing by 444 colonies per day at this point in time. Questions? This doesn't have to be bacteria in a dish. This same sort of model applies to a lot of different scenarios. Who's LECOM pre-med? How do you measure blood pressure? Say again? That's pulse. Systolic and diastolic. How do you measure it? Talk to me. The cuff, right? You listen at the elbow and you squeeze the upper arm until you can't hear the heartbeat anymore. And what you've just done is you figured out how much pressure you have to put to silence the compression of the ventricle, because that's the strong part of your heartbeat. Then you release that slowly. You listen for when the sound comes back. That's your upper number, your systolic blood pressure. Keep listening until you can hear the second part of the heartbeat, which is the compression of the upper part of the heart, the atrial compression. That's your lower number. That's the diastolic. After which point they just open up the cuff and you go, and everything feels better because you're not squeezing your arm like there's no problem. The sphygmomanometer, the blood pressure cuff, is only about 120 years old. Do you know how they used to measure blood pressure before that? By measuring how fast the fluid in your vessels moved. By stabbing you with a sharp glass tube and watching how high up your blood pressure pushed the blood in the tube. When you consider the flow of fluid in any tube, including blood in a vessel, there are a bunch of things that tell you how fast it's moving. We make some assumptions about the flow not having any turbulence in it for the moment. To make our lives easier, we're going to assume that the fluid is all moving in the same direction. There's no swirling, no weirdness like that. That's called laminar flow. And laminar flow is a very interesting behavior because the closer you are to the edge of the tube, the slower you go. The closer you are to the middle, the faster you go. The same thing occurs in hoses, plumbing pipes, even in fluid like the air. Hydraulic lines that use air pressure work this same way. So air hammers and torque wrenches for automotive parts, they're on the end of air compressors. Same idea for laminar flow. Jean Pucelle came up with this relationship that says that the velocity is related to, there's a whole bunch of letters in here, what the hell is going on? P. P is the pressure on the end of the line. Capital R is the radius of the vessel. Little r is where I am relative to the center. So when little r is small, I'm very close to the center. When little r is close to capital R, I'm close to the edge. 4NL. L is the length of the tube. N, eta, is the viscosity of the fluid. How sticky is your blood? If you are well hydrated, that will be a low number. If you are dehydrated, that will be a high number. Things like high cholesterol and plaque impact the viscosity of your blood. This is why people take things like low-dose aspirin and blood thinners to make the blood move smoother. We could ask, how different is the speed at the center versus the speed at the outside? As I get closer, my velocity slows down as I get closer to the edge of the tube. This is why a narrowing of the artery is a problem. Arteriosclerotic plaque, anybody? Useless. I'm trying to prevent a stroke. If I take the derivative of this expression with relationship to R, what I get is exactly that measurement. How fast does the blood slow down when I'm at the center versus when I'm at the edge? The little r, because capital R is fixed by the blood vessel. Little r depends on where I am, right? Capital R, N, L, and P are assumed constant in this equation. I'm only looking at where I am. The result is called the velocity gradient. And if you look at these arrows right here, you see how they're slanted? They make a cone shape, this triangle. That's the velocity gradient. When the velocity gradient is fairly sharp, then there's a lot of slowing towards the edge. And when it's fairly upright, then there's not a lot of slowing at the edge. A lower gradient, a more vertical slope, is a good thing health-wise. And we can measure the speed of any fluid in any tube. Now, here's the best part. This same model applies in other places. I'm going to change this picture from a blood vessel to a road with multiple lanes in it. The center of the road is the median between one side and the other, right? Well, that means the closer I am to the center, the further away I am from the edge, the faster I'm going. On and off traffic is on the right. Faster traffic stays to the left. This same equation works to discuss traffic flow. How the hell do you get from blood vessels to traffic flow? Well, it's exactly this same model of slowing down out at the edge. Pedestrian traffic on sidewalks. Useless. I don't care what you're studying, there's a derivative there. I'm the first person to tell you that I see calculus everywhere because I'm a calculus person. And the lens through which you see the world depends on what you study the most. I had somebody ask me, when I said I could find a derivative in any field, where can I find it in art history? And he thought he was going to stump me. And I said, how do you tell how old a painting is? I carbon date the paint. Carbon dating? The hell's carbon dating? Once again, I'm back to chemistry. C14 versus C12. Two isotopes of the same atom, right? Carbon 14 is unstable. It spits out 2 protons and 2 neutrons and decays into carbon 12. That's called alpha particle emission, I believe. And so carbon 14 is radioactive. As long as a carbon item is alive, it's metabolizing items into carbon. And those carbons are equally likely to have the same ratio of carbon 14 and carbon 12 as their surroundings. But once something is dead, it stops being able to change carbon from one form to another, and the amount of carbon 14 starts to decay. And so I can tell how old something is by the ratio of how much C14 is in it. In the Second World War, the Nazis stole a lot of art, and they tried to sell it to make money. Well, I think it was in the 1960s, A gentleman was arrested for having a Vermeer. Vermeer. Somebody look this artist up. Vermeer. When was Vermeer alive? 17th century. So this is a 350 some odd year old painting, right? They arrested this guy for having a Vermeer that was stolen and that he'd sold it to the Nazis. And he said, no, I didn't sell the Nazis a Vermeer. I sold them a fake. I made this. I ripped off the Nazis. How did they prove it? They dated the paint. Not the canvas, not the frame, because he'd actually taken a 16th century canvas and a 16th century painting and scraped it clean. He made the paint. And tempera paints are made with egg yolks. And eggs are alive. They metabolize carbon at a different rate. Art history. I don't care what field you're studying. There's a derivative in there. A cost equation. Cost, C of X, is total cost of X units. So if I make 1,000 somethings, I'll tell you how much it costs. So we think of cost as having two parts: fixed costs and cost per unit. In its most basic idea, you can think of fixed costs as things like the rent on the building, the price of the machinery you use to make whatever you're making. What are we making today? Graham cracker? Fine. Okay. My fixed costs. I had to buy the building. I had to buy the production facility line, right? So I have my miller, I have my grinder, I have my mixer, and I have my extruder. And I have my oven. Got to bake my graham crackers. And then at the end of that, I have the separator and the packaging. But per graham cracker, I have to buy flour, I have to buy water, I have to buy boxes. So all of that is cost per unit. But fixed cost, I only had to buy the building once. Only buy the oven once, I hope. So in the most basic sense, I can think of this as a constant here, and then some number times X. That makes this equation a straight line. This is the simplest type of cost model. There are more complicated types of cost models that look like more and more complicated equations. But then I can take the derivative here. Wait a minute, this is a straight line. What's the derivative of my cost function? Whatever the slope of that line is, right? That's called the marginal cost. Because if I want to add one more unit's worth of graham crackers, I just have to pay that much. If I have a more complicated equation, I'd just be taking the derivative. In general, marginal cost is C prime of X. Now that's change in cost per change in units. And really, that's the cost to make one more. From whatever my current production level is, that's the cost to add one more unit. Because that would be number over 1 as a slope. Here is a slightly more complicated cost equation. You can see it's a cubic equation that is still roughly increasing over time, which makes sense. The more graham crackers I make, the more expensive it is. Let's suppose my production line is right now making 15 units worth, and I want to go to 16 units. So I go to my accounts and I say, how much is it going to cost me to move from 15 units to 16 units per production run? Well, I can give you an exact value. I can say the exact value would be C of 16 minus C of 15, right? Grab your calculators. Let's find out what this cost is. If I graph this on a sufficiently large window, you can see over time, as I make more stuff, my costs go up, right? But notice what's going on right here in the middle here. There's a spot where I can make more. My cost actually goes down. Why would that happen? There's nothing about sales in here, so I'm not talking about breaking even in any fashion yet. Breaking even is usually about revenue in and costs balancing each other. So I don't have any revenue at the moment. I'm just dealing with costs. Why would, as I make more of something, my costs go down a little at some point? I don't know what you mean by that. Then hold that thought. Mel? Say again? There's nothing about demand and supply in here, unfortunately. But I'm just talking about costs. If my demand went down, I would expect my revenue to go down. Revenue's not up here. If I'm only producing a couple of something, then it's probably a very labor-intensive product, right? But as I get more and more, I get more efficient at things. So my production ramps up, and all of a sudden I can do things in a better fashion. And there's a little dip in cost where my efficiency gets better. But then, oh yeah, then my marginal costs start to go up because I'm making more stuff and my costs go up overall. So to me, if I'm just concerned about costs, there's a sweet spot somewhere in here. I don't know what it is at the moment. We'll figure out how to find it later. But I was at 15. By the way, this is a very large window from 10 to 30 and from negative 100 to 1,000. I was at 15. Hit trace, put in 15. The cost of making 15 units is 492.5. The cost of making 16 units is 496.8. A difference of 4.3. But I can approximate that. My marginal cost is a derivative, right? So let's take the derivative of that expression. What is the marginal cost? at 15. I need a derivative. And now I put 15 into that. And we get no, it's just supposed to be close. You said it was 4, it actually is, you said it was 3 and change, it's actually closer to 4 and change. Remember, my marginal cost represents a tangent line. So why was this off? Let's go back and look at our picture. It's not a straight line there, is it? It's starting to bend up. So my tangent line is going to be under the curve as it starts to bend up. My tangent line is a little low by comparison. Now, in this case, if I was actually a business person, I'd probably want that first number rather than the second. But a lot of relatively easy to calculate events in a business are marginal events. And so you will often see discussion of marginals done in business settings. They're called marginal analysis. And then we have marginal cost. I've got marginal revenue. I've got marginal profit as well. We can do all of these things, provided we have equations for cost and revenue and profit. All of these can be balanced in that way. Finding that good point where our money is best spent is a useful idea. Questions? There are dozens of applications in here. The spread of a rumor. Grows in exactly the same way our bacterial colony grows. It might not double every hour, but it certainly spreads through the population in that fashion. So does an infection. When we talk about learning something, in psychology, my proficiency versus time tends to look like this, where up here is 100% good, and down here is 0% good. In a very real sense, in order to get good at anything, first you have to suck at it. And you have to get to the point where you're a little bit less sucky. And then all of a sudden, that slope increases. And you're better and better and better in a very short period of time. And then that starts to taper off and you're as good as you can be at whatever this is. I don't care whether you're learning calculus or how to tap dance. The same thing is true. Typing speed, juggling proficiency, speaking a foreign language, and learning calculus all follow this elongated S sort of pattern. That shows up in a lot of models as well. So we'll talk about that more once we get back from break. Tomorrow is question and answer day. The homework is due when we get back from break. So if you haven't got it done yet, you should be working on it, or you're going to be working on it over break, and that's going to wreck your break. Let's not do that. I will see you all tomorrow. Have a wonderful rest of your day.